10.4 Comparison Tests. The outline of this video is as follows. We will start by introducing a fundamental tool for determining series convergence, called the direct comparison test. This test allows us to compare a series with unknown behavior to one whose convergence is already known. Next, we will explore a more powerful and often easier to use variation, the limit comparison test. This second test is particularly useful when dealing with series whose terms are rational functions of the index n. Finally, to solidify these concepts, we will walk through several worked examples demonstrating how to choose an appropriate comparison series and apply each of these tests effectively. We are about to learn a powerful new technique for determining if a series converges, called the comparison test. This method works by comparing a new, unknown series to a series whose behavior we already understand, like a geometric series or AP series. The core idea is very intuitive and works for series with positive terms. First, if you can show that your unknown series is smaller than a known convergent series, meaning each of its terms is less than or equal to the corresponding term of the convergent series, then your unknown series must also converge. It is trapped below a finite value. Conversely, if your unknown series is larger than a known divergent series, then it must also diverge. If it is always bigger than something that goes to infinity, it must also go to infinity. In short, we can determine the fate of a complicated series by comparing it to a simpler one. This section will formalize these ideas into two specific methods: the direct comparison test and the limit comparison test. The comparison test is a powerful and intuitive tool that lets us determine if a series converges by comparing it to another series whose behavior we already know. The test requires that all the series terms are non-negative. The test has two main parts. First, for convergence, let us say we have a series we are testing, the sum of a sub n. If we can find a second, larger series, the sum of c sub n, that we know for sure converges, and each term a sub n is less than or equal to the corresponding term c sub n, then our series must also converge. It is effectively being squeezed from above by a series that adds to a finite number. Second, for divergence, if we can find a third, smaller series, the sum of d sub n, that we know diverges to infinity, and our series a sub n is always greater than or equal to it, then our series must also diverge. It is being pushed up to infinity by the divergent series below it. In short, a series converges if it is smaller than a known convergent series, and it diverges if it is larger than a known divergent series. To build a strong intuition for the comparison test, we can visualize the terms of a series as the areas of rectangles. This approach helps make the logic of the test very clear. Imagine we have two series with positive terms, which we can call a sub n and c sub n. Let us assume that for every n, the term a sub n is less than or equal to the term c sub n. In the figure, this is shown by a set of shorter rectangles representing the terms of a sub n and a set of taller rectangles for the terms of c sub n. The sum of a series is then the total area of all its corresponding rectangles. Now suppose we know that the larger series, c sub n, converges. This means the total area of all the taller rectangles adds up to a single finite number. Since each rectangle for a sub n is shorter than its counterpart for c sub n, the total area for the series a sub n must be less than the total area for the series c sub n. It is impossible for the sum of the areas of the shorter rectangles to be infinite if they are all contained within a finite total area. Therefore, if the larger series converges, the smaller series must also converge. This slide shows how to apply the comparison test using two important examples, one for divergence and one for convergence. First, let us examine the series with terms 5 over the quantity 5n minus 1. For large values of n, this term behaves like 1 over n, which suggests comparing it to the harmonic series. We know that the denominator 5n minus 1 is always less than 5n. When we take the reciprocal, the inequality flips, so 1 over the quantity 5n minus 1 is greater than 1 over 5n. This means each term of our series is greater than the corresponding term of the divergent harmonic series. By the comparison test, our series must also diverge. Next, consider the series with terms 1 over n factorial. To test for convergence, we need to find a known convergent series whose terms are larger. The key insight is that for n greater than or equal to 1, n factorial is greater than or equal to 2 to the power of the quantity n minus 1. Taking the reciprocal reverses this inequality. Thus, 1 over n factorial is less than or equal to 1 over 2 to the power of n minus 1. The series formed by these larger terms is a convergent geometric series. Since our series terms are smaller than those of a convergent series, our series must also converge. The direct comparison test is a powerful tool, but finding the right inequality can be difficult. To address this, we will introduce the limit comparison test, which is often much easier to apply. The main challenge with direct comparison is that you must algebraically prove an inequality between the terms of your series and a known series. This can sometimes be surprisingly complicated. The limit comparison test offers a more straightforward approach. Instead of a strict term-by-term inequality, it examines how the terms of the two series behave relative to each other in the long run. As n approaches infinity, it does this by calculating the limit of their ratio. This method is especially effective for series whose terms are rational functions of n, such as one polynomial divided by another. The key idea is that if the terms of two series are proportional in the limit, then both series must share the same fate. They either both converge or both diverge. Now let us examine the second case of the limit comparison test, which applies when the limit of our ratio is 0. This situation tells us that if the limit as n approaches infinity of the fraction a(n) over b(n) equals 0, it means that for large values of n, the terms a(n) are becoming significantly smaller than the terms b(n). You can think of the sequence a(n) as shrinking to 0 much more rapidly than the sequence b(n). Because of this relationship, if the series formed by the larger terms, which is the sum of bn, converges to a finite number, it effectively puts a cap on the series formed by the smaller terms. This forces the sum of an to converge as well. It is very important to remember that this is a one-way implication. If the comparison series, the sum of bn, happens to diverge, this test gives us no information at all about the series of a(n). The key takeaway is, if the limit of the ratio is 0, convergence of the denominator series implies convergence of the numerator series. Let us walk through two examples of the limit comparison test in action. Both examples use part 1 of the test, where we check if the limit of the ratio of terms is a finite, positive number, which tells us that both series either converge or diverge together. First, consider the series with terms an equals the fraction 2n plus 1 over n plus 1 squared. For large n, this term behaves like 2n over n squared, which simplifies to 2 over n. So we compare it to the divergent harmonic series, where bn equals 1 over n. The limit of the ratio an over bn is 2. Since 2 is a finite positive number and the harmonic series diverges, Our original series must also diverge. Next, let us test the series with terms an equals 1 over the quantity 2 to the power of n minus 1. For large n, this behaves like 1 over 2 to the power of n. We compare this to the series with terms bn equals 1 over 2 to the power of n, which is a convergent geometric series. The limit of the ratio an over bn is 1. Since 1 is a finite positive number and our comparison series converges, the original series must also converge. The key is to simplify the original term to find a familiar series to compare it with. In this example, we will test a series that includes a natural logarithm term. The question is whether the sum of the natural log of n over n to the power of 3/2 converges. The key idea is that the natural log of n grows very slowly, even slower than any small positive power of n. This suggests we should compare it to a convergent p-series. Let us choose our comparison series, b sub n, to be 1 over n to the power of 5/4. This is a convergent p-series since the exponent 5/4 is greater than 1. Now we compute the limit of the ratio a sub n over b sub n. After simplifying the fraction, we are left with the limit of the natural log of n divided by n to the power of 1/4. This is an infinity over infinity indeterminate form, so we use L'Hopital's rule. The limit becomes the limit of 4 over n to the power of 1/4, which is 0. Because the limit is 0 and the comparison series converges, part 2 of the limit comparison test tells us that our original series also converges. Let us summarize the two comparison tests to help you decide which one is best for a given problem. The direct comparison test is conceptually straightforward. You simply test if the terms of your series are smaller than those of a known convergent series, or larger than those of a known divergent series. The main difficulty, however, is that you must rigorously prove this inequality holds, which can be challenging. The limit comparison test often provides a more direct route to the answer, especially for series whose terms are rational or algebraic functions of n. This test cleverly replaces the need to prove an inequality with the often simpler task of calculating a limit. For both tests, the general strategy for choosing a comparison series is the same. Look at the dominant terms in the formula for your series, particularly for large values of n. These terms will point you toward a simpler p-series or geometric series that should behave in the same way. The key is to choose the right tool: direct comparison when an inequality is obvious, and limit comparison for more complex algebraic forms. To wrap up our discussion on comparison tests, let us consider two review questions to solidify these concepts. First, look at the series defined by the sum of the fraction n squared minus 10 over the quantity n to the fourth plus n plus 1. Which test, the direct comparison or the limit comparison, would be easier to apply here? And what would be a good series, the sum of b sub n, to compare it with? As a hint, think about the dominant terms for large values of n to find a simpler function that behaves similarly. For the second question, suppose you use the limit comparison test. You compare your series, the sum of a sub n, with a known divergent series, the sum of b sub n. After taking the limit of the ratio a sub n over b sub n, you find that the result is 0. What can you conclude about the convergence of the sum of a sub n in this specific case? And what is the reasoning? Refer back to the formal statement of the limit comparison test to see which part applies. Take a moment to pause and think through your answers to these two problems.